Alright, so in activity 9, we're going to be solving systems of two equations. You should have done this, but basically when you did this in Algebra 1, you were doing it with two linear systems. So you had like x plus 7y equals 10, and then 2x minus 3y equaled 20, and you were basically seeing when those two things intersect. Because so in algebra, when we're linear, what kind of lines do we have? Straight lines, right? So I have a line here, correct? And that's one of my equations. What did I tell you a graph is? What is a graph? It's a visual representation of all the answers. So everything that is on here, if you take this x and this y, what's it going to do to that equation? It's going to make it true. If you take this x and this y, what's it going to do to that equation? Make it false. So every one of these ordered pairs would do what to the equation? Make it true. You with me? Well, then I have a second equation, right? And it goes like this. And every ordered pair on here would make the equation for this one true, correct? But this one right here would do what? This one right here, where they're both touching, what would that one ordered pair do? It would make both equations true. Do you understand? It's on both lines. So if I put this ordered pair in, it's going to make this equation true. If I put this ordered pair in, it's going to make this equation true. And that is what we're looking for when we're doing systems. We want one ordered pair, one x and y, as an ordered pair, that are going to make both equations true. See, when I have like 2x plus y equals 10, there's a whole bunch of answers for this. Because as my x changes, my y change, correct? And that means that's why we have all these different ordered pairs. There's an infinite amount of answers that can work. Depending on what your x is, the y will change to make it true. Like if I said x is 4, right? 4 times 2 is 8. So what would y have to be? 2. Are you with me? So my ordered pair would be 4, 2. But what if I said x is 3? 3 times 2 is 6 plus what is 10? Do you guys get where I'm getting these ordered pairs? So as my x changes, my y changes. You with me? But when I do this, and I have 2 of them, and I said I want an x and a y that makes both of them true, see, there's an infinite amount of solutions for this one, right? That's with all these ordered pairs. There's an infinite amount for this one. That's what all these pairs would be. But sometimes there's one that makes both of them true. Are you with me? Now, why did I say sometimes? What can happen with lines? What happens with this line and this line? Why? Because they're what? So as soon as I know that they're parallel, I know they're never going to touch, and I can say there's no solution for those two. There's never an ordered pair that will make both of them true because they're never going to touch each other. Are you with me? What would happen in that case? What do I know about their slopes? How do you know parallel lines? They have the same slope, but different y-intercepts. If when I was talking linear, here's this guy and this guy. This guy has got this y-intercept, this guy's got this y-intercept, but they have the same slope. There's no solution. So right here, are those guys going to have a solution? No, because I look right here and I go, same slope, different y-intercept, they're going to be parallel to each other. There is no solution that's going to make both of them true. They're never going to touch. Are you with me? There's another one because I can make different things look, I can make it look different, but it really is the same equation. Here's what I mean. and this is how they can play games with you a little bit, but it's really what happens in real life. And they say, hey, when did these guys touch? Well, the problem is, it's not, this is in what form? This is in slope-intercept. This one is in what we call like standard form. So I can't tell its slope right now. So what I do is I can change this. I know I'm allowed to change things in math. That's what this whole year's been about. So I'm allowed to change the way it looks. So what I do is I go, you know what? I'm going to make this say y equals down here. So if I was going to do that, I get everything away from the y. You with me? So I would like add 6x, and it would become 2y equals 6x plus 14. You with me? Now what would I do? Divide by 2, divide by 2, divide by 2. And when I do that, I get y equals 3x plus 7. What do you notice about this one and this one? And so they would look like this. You would draw the line, and then you draw the other line on top of it. So how many solutions do they have? Infinite amount. Every solution that works in the first one is going to work in the second one. So for systems of equations that are linear, you have a couple options. You have one solution that looks like this right here that we first did. Yes? You have no solution because the two lines are parallel to each other with different y-intercepts. Or you have infinite amount of solutions, which means whatever ordered pairs work for the first one or have to work for the second one because they're the same line. They just, in the beginning, started out looking a little different. Are you with me on this? Okay? So that's what you should have learned, and that's a basic overall of what you should have learned from Algebra 1. I believe we even covered it a little bit at the beginning of the year. All right, so now we're going to apply this to some other stuff. We've learned some more stuff. We've learned about quadratics. All right, so one way to do this, which is the worst way, just so you know, is by doing it by graphing. And why is the worst way to do it by? It's a good way to get an estimation, but why is it the worst way? What do we learn that we have a lot more of in real life? Are numbers always 1? Are they always 2? What can they be? Like 5 pi over 7. It's one of the numbers that we right? We've talked about that kind of number, right? Well, is that going to be nice and easy to see 5 pi over 7 is the solution for my example? No. So the reason graphing isn't the best is because it doesn't give you exact answers every time. It's a good way to get an approximation. I can say, hey, this is about where I know it's going to be, but it doesn't give me that hard answer that I need sometimes. You with me? All right. So first off, they say you would like to take a taxi airport, and this is a real world problem. Okay? Taxi, right? Am I going to Uber or am I going to taxi? Which one's going to be cheaper for me? Hey, some of you are going to go, I don't really care. You're going to spend more money and waste more money. Some people who take the time to figure this out save more money, right? So one cab charges $2.60 plus 20 cents per sixth of a mile driven. The other one charges a $5 fee right off the bat, but only 10 cents per sixth of a mile. Are you with me? So obviously you can tell if I'm taking a shorter drive, this one's going to be the way to go, right? But if I'm going from like here to Orlando, this one's going to be the way to go. You guys talking about? And so what we're going to figure out is at what mile is it going to be better for me to take the second one than the first one? You with me on this? That's a real world problem, correct? Does this have to be taxi driving? No. Screen printing, right? I'm going to buy a t-shirt for, I don't know, say students who barely survived my class. Okay? The first one charges a screen print of $20, but only $10 per shirt. Right? Another one charges only a $15 screen print, but it's $12 per shirt. Does that happen in real world? Absolutely. And so depending on how many shirts I'm going to order, there's going to be one that's better. And so same thing here, right? So what they did is they graphed this. The way that you graph this is you would use your intersections, right? This right here is my y-intercept, right? There's 2.6. Does everybody see that right there? This is my other y-intercept. That's why they put it at 5. And then how do I go up and over? I use my what? What do I use to graph? How do I get from one point to another point when I'm on linear? My slope, which is right here. But it's not so nice the way that it is it? So how can I change this? This really means 2/10. Understand? Or 1/5. You with me? Now, if you look at this right here, this is with the numbers being a little bit funky. It is not the best thing. Let's go to right here, maybe. Is there another one that's easier? Let's use the 5 because I know it's. I'm going to use this one to explain, and then we'll come back to the other one because it starts with easier numbers. Do you see that guy right there? Okay. So what is the 5s? It's 1/10, correct? Okay. So look what happens. And it's not even perfect either. It goes every $1, right? It's going to cost, how far can you drive? Every $1, this is dollar, you get to drive what? Does that make sense? Right? Because 10th, actually no, this is a 1/6 of a mile. Let's see how we're going to do that. Oh, right here. Do you see that they did this in 1/6 of a mile already? So this is, what is this? 4/6 of a mile. You with me on that? That definitely makes it, this 1/6 of a mile makes it a pain in the butt. So what they did is they made the bottom just in 1/6. So that helps us out with our counting. You with me? So 1, and they went over 10, and it's hard to tell because it looks like it hits right there. But does that make sense? Goes up 5/10, or up 1/10, up 1/10. Does that make sense? Yes? Okay. Same thing they did with this one. They're going to go up 1/5, we said. And again, this is not the best way to do this because it's just going to give us an estimation. Right here, it looks that about, you would get 24/6 of a mile. You guys get what that means, right? You would get 24/1/6 of a mile. You following me? So what does that mean? How many miles did you actually travel? 24 divided by 6 is you actually travel 4 miles. Does that make sense? At about 4 miles, the cost should be equivalent. So it does. If you're going 4 miles, you can call the first cab company, you can call the second cab company. It's going to cost you the same amount. You with me? After 4 miles, it's going to be smarter to choose this guy. If you're going less than 4 miles, it's going to be smarter to choose this guy. Can you see that on the graph? You with me on this? Okay, so let's see. They're going to probably ask us some questions like that. Estimate the solution for this and justify your reasoning. The solution to the system, remember, the system is where they're both equivalent, is 24. Isn't that what we just said? Which actually was 4 total miles. This is the x-coordinate of the point The y coordinate of this point is between 7 and 8. So they go over and they say at 4 miles or 16ths of a mile, it's going to be right between here. It's going to be about $7.50 for that total ride. Does everybody understand how it's between? This is the cost in dollars. This is how far you've driven. You with me? All right, now here's the real way that I like. This is where you have two options. You can do what is called substitution, or you can do what is called elimination. Do you guys remember hearing those words? I'm pretty sure we talked about this. We talked about it a little bit at some point at the beginning of the year. Okay. Substitution is when you take something out and you put something else in its place. Why are these really good candidates for substitution? What does this say? Y equals all alone, correct? What does this one also say? And so what I can do is I can take this y out and replace it with what this y equals. You guys see, this says y equals. And right here, this is what y equals, correct? I can take this y out, and I can put this in its place. And that's exactly what they did. That's called substitution. And why? So remember what we talked about? The reason we can't solve this guy? Why can't I say, what's the answer to this one? Why can't you give me an answer? Why can't you just say 5 is the answer to this equation? How many variables are there? So what did we talk about? As my x changes so there's not just one solution, right? If I go this many miles, this is how much it's going to be. You change your miles, the amount changes, right? There's not one solution. There's ordered pairs. That's why we have a graph. That's why it looks like a line, right? Because it's like, hey, if you go this far, this is how much. Well, if you go this far, this is how much. You go this far, this is how much, right? There's not one solution. So you have to get it. There's two variables. Are you with me? But now, if I can get it down to just one variable, you guys with me? Then I can solve, and I can say x equals. So the goal, whenever you are doing this, is to get it to go to one variable. Because we're trying to say, hey, when are these two things equal to each other? When are they the same? So what I can do is I can replace the y's in terms of x. So now do you see how they took this y out and they replaced it with this guy right here in this step? Now, what variables on this side? What variables on this side? Are there two different variables? No. What can I do with x's? I can combine them onto one side so that I can make it say x equals, which you see right here is what they did, correct? And how many miles did we say it looked like it was going to be, that they were going to be equivalent at? And isn't that what we got when we did the actual math? Now, is it always going to be a nice, pretty number like 24? Could it have been 24 and a half miles? Would that be very hard to see on the graph? Do you understand why this is so much better to do actually hard math? Now, if you're just doing an estimation, like if I don't really care if it's a little bit off, I go, as long as I'm going under 4 miles, I'm going to choose this one if it's over. You get what I mean? Sometimes it depends on which way you're looking at. All right, so this gives me an answer of 24. That's one way. This guy over here chooses the other way of doing it. What he does is called elimination. What does eliminate mean? To get rid of. You're going to cancel out one of the variables. You with me? So what he does is he does a lot of pre-work that they don't show. He moves both these equations around. You with me? First thing he does is he moves this over to this side, which is fine. I would do it different, but he goes negative 0.2x plus y equals 2.6. You with me? He then minuses this over here, so it becomes a negative 0.1x plus y equals 5.6. Now, you can actually add or technically subtract equations together. I will encourage you to never subtract equations together. The reason why is because kids forget that we are subtracting towards the end of the problem. Here's what I mean. I can go ahead and subtract these two. I do not want you doing this. I'm showing you why. This is where kids make mistakes. When you subtract, what are you doing right here? A negative 0.2x minus a what? So what does this part actually turn to? And so you are actually going to add that. Do you see how that's kind of confusing? Also, when you get back here, what do kids do? They forget that they are supposed to be subtracting, and guess what they do? They write this as 2.2, put a 1 here, and make an 8 there. And they add them because they forget you're supposed to be subtracting this guy, and this guy. Are you following me? So what I tell you to do, hold on one second. Here's what I tell you to do. In order for something to cancel out, something out, what should this sign and this sign be? One needs to be positive, one needs to be, well, how can I change one of these signs? What is something I've been trying to tell you? Changes signs, but does not change numbers. There's only one number in the world that can change signs, but not change values. Negative 1 changes signs, but doesn't change numbers. Am I allowed to multiply by anything I want to onto this equation? Yes, you can. As long as I do it to everything, I just change the way it looks. I haven't changed its value. That's what we've been studying all year long. Changing the way things look, but not their value. Well, if I change times by negative 1, that's going to make this a positive, that's going to make this a negative, and that's going to make this a negative. Are you with me? Look what they did right here. Does everybody see a negative 0.2x plus y right here equals 2.6? Yes? Look what they have right here. Remember, what was my 0.1? It was positive. Or it was negative. What did it turn to? Positive. My y was positive. I scratched out and it became a negative. My 5 was positive and it became a negative. Do you guys see where that came? They multiplied this, what I had up here, by a negative 1, which just changes all the signs. And why did they do that? So that when they add, because it's much easier to add because we can see the signs now, when I add these two together, these guys cancel out. Also known as eliminate. I eliminate one of the variables. You with me? There's many tricks in this. They go through, they get that. Now, just because I got x, normally for a ordered pair, I need a x and I need a. So what do they do to find the y? They just take the x that they found, plug it in, and when you plug it in, you can simplify all this and get a y out. And we realize that it's $7.40. The same thing they did over here. When they found an x, what did they do? They plugged it into one of the equations. Now, also known, whenever you take something out to put something else in its place, it's called substitution. They substitute in, and they get that it's 740. It doesn't matter which way you use. This one is called substitution. This way is called elimination. Either way, you're going to get the same answer. Does that kind of make sense? And we'll try to go over a little bit more of this tomorrow. And actually, I'll probably finish this video and put it up online. Questions?